opponent to challenge the problem to the reporter. That's it. Okay. Now, the representative of each team come over and write down the name.
the problem statement. When a drop of water mixture is deposited on the surface of a hydrophobic liquid, the resulting drop is sometimes broken into smaller droplets. Investigate the parameters that affect the fermentation and the size of the final droplets. So we fill the main focus with these problems. Calculate the maximum radius and expansion rate of the droplet depending on the relevant parameters, and how to estimate the lowest concentration of certain phenomena. So here's the outline of our presentation. I'm going to go for introduction, and I'm going to go through theory, and then it will be the experimentation and discussion, and finally the conclusion. So let's begin with the introduction. With a jar composed of water and isopropanol and ink dropping on the surface of the oil, the initial model drop, the strategy begins to fragment and becomes a standing fingers of smaller choke droplets out from the perimeter over time. The unstable model drop completely evaporates, and the entire solution forms a sea of very small stable droplets. Now, in our experiments, the droplets have uniform composition initially, but after a short time, some of the alcohol evaporated, and the denominator is relatively deep, and the surrounding area is shallow. So the evaporation rate, the depth of the mixture is different. Therefore, in comparison, even if the same amount of alcohol is evaporated, the rim concentration will decrease more. And that sets up a surface tension gradient, and creates low surface tension at the center and high surface tension at the rim. And the surface tension gradient cause the water molecules at the center being pulled by the water molecules at the rim. So here's a video of our experimentation playing at double speed. After spreading air happened into small pieces, the droplet will finally shrink back. And the reason for that is the initial kinetic energy between the droplets. And this is something called the Marangoni effect. And this phenomenon happens whenever there is a surface tension gradient on the outer surface of a liquid. And we think it's the droplets sending out small droplets, but not a circle by circle, is because the radius scale is ability, and it will cause the droplets to break into small drops. And let's take a look at this more obvious example. The molecular attraction causes water to be separated, and this is a picture before and after adding the mixture. As you can see, all the peppers gather to the edge, and we see the reason is that the salty water in the center has a lower surface tension. So here's our theory. First, we focus on the forces of the motion, and we combine all the forces that are proportional to the radius. First, k is a function of t. In other words, it is the time-dependent spring parameters. F equals to coefficient k multiplied with radius. And as for the middle term, it is a total hydrostatic force, and the hydrostatic force is caused by the pressure loading of a liquid acting on the submerged surface. And because we want to focus on the connection between the radius, so we reform the formula, and after arranging, the middle term has been rewritten as k naught multiplied by r naught quartet divided by radius cube. And as for the last one, it's a damping force, or frictional force. And minus means for its direction, and minus b stands for this according to Brennan's formula. And for this formula, we can easily find out that this motion is associated with the radius. So with the decreasing radius, the force in the negative direction will get weaker, and the force in the positive direction will get stronger. And that means the droplets will finally stop exploding in the end. And for here, we got 3 kinds of surface tension, which between oil and air, mixture and mixture and oil. And we define the parameter S as a surface tension between oil and air minus which between mixture and air and mixture and oil. And we can know that the surface tension can be sort of the potential energy per unit area, and the surface tension of these 3 solutions can be seen as the surface energy. And if the S is smaller than 0, the droplets will expand, or even if it expands, it will shrink back. And the reason is that the more open it expands, the greater the potential energy is. So for here, this is a formula that shows how the oil volume affects the radius and the expansion rate. As you can see, S stands for the height of the oil, and with a higher H, the spreading time will be shorter, and that means the expansion rate will be higher. And for this, we got the small summary for our series. First, we combined all the forces and got the formula, and we found out this motion is associated with the radius, and we got the surface tension, and that will help us to find out the lower concentration. And then we got the formula that shows how the height of the oil affects, and we'll have the result of the height of oil in our following report. So here's our experimentation. And this is our setup, and this shows how we actually do the experiments. We use a barrette to make sure all the droplets have the same size. And this is a picture of our experimentation. And before introducing our experimentation, I should define some nouns in it. First, when we drop a droplet on the oil, we call it the initial droplets. Then, wait until there are small droplets on the edge, we call it the maximum droplets. Then wait for 10 minutes, we record the result and call it the final droplets. And the final center droplets means the average of 4 to 10 12 droplets at the center. And here's our background experiment. We measure the surface tension. So for our steps, we make a ring with the iron wire and measure its mass. And then we put the liquid to be cast in the ring in the container. And then we measure the total weight and pull the metal ring out slowly. And then when the liquid film separates from the ring, we record the smallest reading on the electronic scale. And then we minus the weight of the ring and then divide it by twice the length of the ring. Then we get the surface tension of the liquid. So here's our experimentation. We've got 4 variables. There are the concentration of the mixture, the type of oil, the type of alcohol, and the thickness of oil. So we choose to change the concentration of the mixture and the alcohol because it affects the evaporation rate, and the evaporation rate may affect the surface tension gradient. And we choose to change the different surface tension of the oil and the thickness of oil is because it affects the expansion rate of the droplets. And if the expansion rate slows down, there will be more time to evaporate and create the surface tension gradients. And we think temperature also affects the result, but these variables are not explored in our experiments. So here's the maximum radius of which-drum oil under different concentration. We cannot see remarkably changing between 10 to 30%. But after 40%, we found out the numerical value quite sharply. So we tried the experiment in 30 to 40% range, and we tried the experiment with 35% and 37.5% to try to find out the lowest concentration. And we found out the lowest concentration was about 37.5%. And as you can see, after the lowest concentration, the numerical value of final droplets becomes so small and even close to zero. And we think the reason is that the droplets fragment into tiny chill droplets, so the average of them is so small. And we got another variable, the type of oil. We got castor oil, sunflower oil, which-drum oil, and brown rice oil. And this is the maximum radius of all kinds of oil under different concentration of the isopropanol. And as you can see, for the different kinds of oil, it climbs sharply at different concentration. And we guessing the results are associated with the surface tension. We measure the surface tension. But what's the connection between the surface tension and the climbing concentration? So let's go back to our empirical data chart again. And as you can see, the castor oil, which has the highest surface tension, starts to climb sharply first, while the brown rice oil starts to climb secondly. So we can know that the surface tension has a positive correlation with the lowest concentration. So we've got another variable, type of alcohol. We compare isopropanol with ethanol to do more in-depth research. And as you can see, the lowest concentration of all kinds of oil under isopropanol is much lower than under ethanol. And we think it is because the rate of evaporate difference between the isopropanol and the ethanol. And you can see another difference in this chart. The isopropanol spacing between the lowest concentration is much lower, and we think it is because of the different solubility caused by different polarity. And this is the radius under different volume of oil, and we've shown that formula to show how the height affects the expansion rate. And as you can see, the data of 5 millimeters always have the highest data, so we can know that the thickness of oil and the expansion rate shows a positive correlation. So here's our discussion. For the discussion, I'll tell you the connection between the surface tension and the lowest concentration. So by measuring the surface tension on the different concentrations of the mixture, we can additionally calculate S, and we can find out the lowest concentration by finding out where S is bigger than 0. And so we compared our theoretical data with the experimental data, and we found out there is a small range between them, and we think it is caused by the radius stability. And here's our conclusion. So for the conclusion, we have the conceptual understanding. We observed the phenomena and investigated with the Marangoni effect and the surface tension gradients. And for the experiments, we got 4 variables. We got the concentration of the mixture, and we found out that we can observe in the higher concentration but not in the lower concentration. And we got the surface tension of the oil, and we find out that when the surface tension of the oil is higher, we will observe the droplet is floating at lower concentration of the alcohol. And we've got the type of alcohol, and we found out that the lowest concentration of isopropanol is much smaller than ethanol, and we think it is caused by the different evaporation rate and solubility caused by the calorities. And for the thickness of the oil, we found out that when the oil is thicker, we've got higher expansion rate. And here's our references. Thanks for your kind attention.
Okay.
So, our first question for you is, can you assume that the droplets are the same size when you drop on the liquid?
We use for our setup, I tell you that we use a barrette to measure each droplet may have about the same size.
Okay, so do you think that the coloring will affect the droplet size or?
Because we use so small amounts of coloring, so we think the coloring may not affect our results.
Okay, so on that, do you consider the evaporation in the theory?
Consider the evaporation.
Yes.
In our theory? No, we didn't consider it in our theory.
But you mentioned it before. Okay. Next thing, did you control the position that you drop? I mean, like on the plate that you drop.
We all drop
In the middle.
in the middle.
So I think next time you will be a little concerned about that. Did you go down all the characteristics that you tried of the oil, like every kind of the oil?
Yes, I've shown the chart that shows all the maximum radius of all the
I mean the characteristic of each oil, like the surface tension or like.
Oh, because they are all vegetable oil, so we think it may have the similar, yes, they may be similar.
Similar
Yes.
characteristic, right? So next thing. Do you have any reasons why you choose a portion of the droplet? Any purpose for like choosing the ratio between the alcohol and water? Like any reasons? Like if you can choose 100% alcohol or 90% alcohol and 10% water, do you have any purpose for that?
So we try 10, 20,
Okay,
30.
answer.
Right, here's the pros and cons of the recorder. The pros is that first, they have a complete theory. Second, they speak loud enough for us to hear. Third, they have a clear data of the experiment and result. And fourth, they show relationship between each data. And the cons are speaking too fast. Because I roughly remember they have 30 more page outside and you can finish it in 11 minutes. Be too fast. Okay, and the next one, not enough understanding time of your theory and project. And I know that you guys have a strong theory, and if you want to show all of us that how do you do it, so, and you explain it, because the theory is too strong, and you have a lot of equations, and we didn't have enough time to understand it. And next one, you can tell the strong relationship between your theory and experiment. And here are the questions that I try to ask you. First, the same size of the droplet. The second, do you consider temperature as a variable? Third, the droplet even. And fourth, do you try to control the position that you drop? Fifth, the effect, do you consider the evaporation in your theory? And next one, do you think the food coloring affect the droplet? And the next, you record the characteristic of each kind of oil. And here are the points to be discussed. Define the state of final. Is that in this experiment, when you drop the droplet onto oil or something else, there are different kinds of states, and then you mention in your result. In the final state, the radius are like several millimeters or so, and you have to define the state of final. And the next one to discuss about is the purpose of choosing this liquid mixture for the droplet. This is the type. And this means that I want to know that if you choose this portion of the liquid that you drop it randomly, or you have a reader for it, and if you have tried before the experiment, before you start to record all the results for the experiment, do you try anything else? And next slide, is there any relationship between these charts? These are the questions followed by the above. And will the fermentation because of hydrophobicity instead of solution? This means that you have a strong theory to explain this. And I want to know that is this a bigger factor or solution is a bigger factor, and you can explain with the theory. And next one, you have to talk more about theory. And because I didn't understand completely. And next, the lithophysics affects the final droplet. Does this factor affect your droplet or not? And did you consider time as a variable of the final fragment? Because in our imagination, we think that the time might affect the final fragment. And when you drop it, when time goes by for like 30 minutes, I think the final fragment will start to change, and the diameter of it will be different from the state of 30 minutes ago. And did you consider height of the droplet? And how will this affect the result? And this is my report. First, can you tell me what's the definition of the state of final, like the time?
I'm showing you in this slide, I tell you that I draw the droplets, then wait for 10 minutes, then we record the result and calculate the final droplets.
Okay, so, and the next question for this is actually, did you consider the time as a variable of the final droplet? Is that the 10 minutes can be different? You can choose like 5 minutes, 30 minutes, or other numbers.
Because we think they may have a small change when we record the result at 1 minute, and we tried the experimentation for many times, and we found out that when we wait for 10 minutes, the droplets may not move much. So we record this result and also the final droplets.
Okay, so as you mentioned, you talked about the result of after 10 minutes.
Yes.
And if we go to another 30 minutes, the result might change. And can you explain it with your theory? You can show me your theory, and then I can explain
Could
it.
you please?
Okay, so as you said, 10 minutes. After 10 minutes, the final droplet will show, and you can you wait another like 15 minutes, and you say then the final droplet will change, the shape or the diameter will change. And can you explain why with your theory?
So after spreading, and I told you that with the decreasing radius, and the droplet may stop moving in the end. So I showed that in this spatial theory, and we found out the droplet will finally stop exploding in the end. And for the explaining for your short question, I tell you that I didn't have a theory between the evaporation rate, but this theory can show the connection between the radius, and we think the evaporation rate may affect the radius. So we show this formula to show why we change the evaporation rate.
Oh, okay. So can you show me the page that you analysis the mechanism with the some force for example.
Some force?
Some for the total force. Show me the analysis of the force. Not this. Yes, it is. Okay, so you consider the okay, so can you tell me why does the surface tension doesn't make the droplet deeper? Like yes, if you show this in your picture, right? The middle part is bigger, is deeper than the other part. And why does the surface tension even this out? Like why won't the droplet be completely even on the surface? And explain it by your figure. Yes.
So there's a droplet, and we show that the warm molecules may be attracted to the edge. So we think the warm molecules gather to the edge, and it may
Make it deeper, right?
yes. And when we drop the droplets at different heights, it may affect the speed of the droplet. It's because the height we drop and the initial kinetic energy.
Okay, so I just see it in your picture. There's a H parentheses R comma T. Can you show me what can you explain what is that, and maybe I will give you yes.
So the parameters we don't in our
You didn't consider that, right? The depth of the middle droplet.
No, we didn't consider that. We just showed this picture.
Oh,
This
just
picture
show-
to tell you that it will create a surface tension gradient, and the surface tension gradient may cause our effect.
So the
Remember
T
that?
is the tension. The H
So
R.
how do we say that again?
This T means time or tension. I mean, you show it in the picture. I want to know about. Yeah, I'm very curious about this result you get.
Sorry, but this is my fault. But these all parameters are not useful
Okay.
in our terms.
Okay, so can you tell me what do you think when you drop it and the time pass by like 40 minutes or more? How will what is the trend of the final fragrance will be like? Like you can show me. I think you can talk about it, like the final fragrance, the smaller droplet at the outer diameter of the big project.
So in our theory, we just think it may stop moving.
It will start moving, right? And okay, can you start to explain your theory from your point? Like there's a I don't remember which page, but yeah. And Fomi theory fits this experiment? Why? The reason why does this fit or the yes, can you explain?
Because we think that fragmentation is caused by the Marangoni effect. So we use the formula. We think it may be the experiment, and we also got the fitting data that in our for our volume.
You started out the data in this case.
Yes, and this is our results. So we think this may be the correct formula that we can use to explain this phenomenon.
Okay, so since we didn't do this experiment and we didn't do a lot of research, can you tell me the restrictions for the theory that we talked about? The restriction, like in which condition you can use like the
So
restriction?
we think we show three formula, and I think in our experiment we can use it all the time.
Can you show me?
Our theory.
Yeah.
You mean this one or the surface tension one?
I think this one. Okay, so let's see. So this is okay. So
And this one shows it because we want to calculate the surface energy. So we use this slide to show you the surface tension.
let's see. Do you have a procedure of solving this equation? Procedure, like every step of your solving steps for this equation. This is the final equation, right? So solving steps, like so we just copy it from the reference.
Yes, because we think this phenomenon attacked by solving things. So we didn't calculate for an exact number for our results. We just have a train of it. So we found out the higher train effect, and with the higher height, we got the higher expansion rate and the lower rate spreading.
Okay, so
So for the summary.
okay, so the experiment with the graph.
So here.
So can you tell me that the relationship between this graph and your theory, and show me a theory that exactly fits this graph or this graph is true?
The theory is.
The theory that explain this graph and why it distribute like this.
So for the surface tension, we found out when our S is bigger than 0, it may be our lowest concentration. And we compare it with our experimental data, and where experimental data is 37.5%, and our theoretical data is about 40%. So we think it may fit our results.
Okay, so what do you think is the error?
Okay, time is up. 也欢迎我这个concluding remarks.
So after the discussion between the reporter, I have a better understanding for the formula, and I know more about the purpose of using different variables and why did they use it. And now I still have a lot of questions about their theory because there's too less of time for me to check and to think about every equation that they have on their slide. And maybe next time we can try this out. We can try out this experiment and have a more understanding of the result and theory of this report. Okay, thank you.
Okay. There are 3 minutes for the reviewer to ask a question.
I want to ask for the progress. How many times do you measure the maximum of the radius? How many times? How many times do you do experiments for
Concentration for 2 times, and we got the average. And because we got a lot of concentration, so each time we did some
Okay, but I still think that you should have an error bar about it. And do do you know the evaporation rate of the alcohol and expanded alcohol?
Actually, we measure it by waiting it to evaporate and see the ingredients. So we measure the alcohol, even the alcohol, water, and isopropyl, other concentration of the alcohol. So we know the evaporation.
Evaporation. So do you know the evaporation rate of the ethanol is 0.15 kilogram per minute? This is relatively small.
We didn't measure the exact number, but we got because we know the isopropyl,
Right, you are serious.
because we know isopropyl is higher than ethanol.
Okay. So can you analyze how the kinetic energy changing in this system? Because we have talked about the kinetic energy.
Because we fix the height, we drop the droplets. So we think the kinetic energy in all our experiments may be the same. So but we didn't discuss about the kinetic energy.
Okay. And what do you think about the kinetic energy in this system?
The kinetic energy for the droplet, drop. Do you mean that the kinetic energy will be drop the droplet?
After you drop.
I think because the height that you drop from will cause the potential energy and wavelength, and some kinetic energy will be consumed by the liquid below, and the net energy will start to stretch the mother droplet. Yes.
Okay. And you have a question about what is the S, the coefficient I showed before. The S, can you show that later?
Yes.
S, I think, you got formula for it, right?
Which one?
Oh, yes. Yeah, this one. How do you derive this formula?
We define the S.
Yeah. Why did you define it?
This because this three circumstances is have opposite side way of the direction of the for the droplet. So we define it for this kind of circumstance.
Okay. And did you?
I have an understanding. Yeah, more clear understanding. Yes.
Time's up.
morning, everybody. I am the reviewer from the Team Energy Fresh. And today the topic I'm going to talk about is the pressure and droplet explosion, the key statement. And within the pressure is mainly focused on the hydrophobic fragmentation and what is so-called final. An overview of the recording, her advantage including clear process graphics, substantial diagrams, and clear thoughts stating the process of doing the experiment, and even have graphics about it. And she tried her best to make sure the initial potential is the same and to eliminate the deviation. However, we've got some suggestions. So the first one is that she didn't mention the exact volume they drew per time. And the second one is the evaporation rate of ethanol and the isopropyl alcohol is relatively small. And the third one, due to number 2, so we didn't think that the evaporation is important parameter in this experiment. And the third one is that she failed to notice the characteristic of ethanol and isopropyl alcohol. And because both of them are lipophilic and hydrophilic at the same time, which is related to the problem statement. And the first one is the spreading coefficients, the relation, is not clear enough. Though we are sure that they have interfacial relations, but I think what she explains is not clear enough. And the fifth point is that without the error bar, it probably means that she didn't do much experiment, and it is not accurate enough. An overview of the component. Advantage including structural suggestions and listed clear project direction. And the suggestions for him is that somehow too much were concentrated on their experiments, and probably he could have deeper discussion. As for the special one, the opponent asked, what's the so-called final, and why did you choose it? The reporter answered, after 10 minutes for the droplets, there might be derivation, because there might be derivation in 5 minutes. And then opponent says that water surface tension uneven can cause this phenomenon. And the reporter asked the Lorentz effect. And opponent asked about, please try to clarify the definition in the formula of S, which is the spreading coefficient. And the reporter no exact answer, though she have mentioned about the interfacial relations between the rates and tensions. But we personally think that is not clear enough, and the reasons are not strong enough too. So here are some missing points that we think that they could improve. So the first one is the accuracy of the size of 100 droplets. And I think she should have the architect scale in her experiments. But when I see in the demonstration video, I didn't see the architect scale. So, and she also didn't mention what to do to analyze the size of final droplets. And the second one is that within the spreading coefficient is the word of adhesion minus the word of cohesion. And the third one is the Young-Laplace equation. And gamma here stands for the coefficient of surface tensions. So this will definitely affect this experiment, but they could have talked about it, but they didn't. And the reviewer believes that the HFB value, which is the hydrophilic and lipophilic balance value,
Time is up. Now it's
is a crucial.
So here's another looking from reporter. All in all, we have learned a lot more about this phenomenon, and we really appreciate the opponent and the reviewer for the great discussion. And for the theory, I think we should do more also to consider the depth of the drop, and we should explain more about the theoretical formula and the parameters which are experiment more, because I didn't explain more about that. And we can add the variables of drop and height of the temperature and the temperature to the theory to describe the initial kinetic energy, because in our experimentation, we just fix the height and the temperature while not changing it, and to see the changing between the results. And for the experimentation, I think we should describe more about the experimentation error, because I just tell the experimentation error, but didn't tell what caused it. And we think we should control the same size of the drop with the bird. And we think that is the most accurate equipment that we can get in our experiment. So and the droplet will be quite stable after 10 minutes. So we think the time is we actually did the experiment that records the 30 minutes of the droplets, and we found out that after 10 minutes, the droplet didn't move at all. And we should add error bars to our graph because we didn't do a lot of experiments to draw a graph, but because we just want to show the trend of it, so we didn't draw the error bars to show how the error will be. And for the reviewer questions, we dropped 0.2 millimeters of the mixture for every experiment. So we fixed it. So here's our remarks and our recommendation.
Now it's the time for any questions from the viewers.
Okay, I have a question. Looking to the reporter's presentation, you mentioned about there is a threshold of concentration around 37%, and you mentioned about it's very close to your theoretical estimation. It's about 40%. How did you get the estimation from your theory, the 40%?
Also, for the theoretical data, we just calculate it with the parameter s. When the s is bigger than 0, we call this the theoretical data that the lowest concentration is, because we think the surface tension will affect very low. So we calculate the surface tension between them and find out the lowest concentration.
And do you have any comment about this statement? Because the reporter thinks 40% and 37% is quite close.
I personally think that is not close, and I don't think that can be derived from the theory.
I think that because the report here mentioned the molecular drop, how much more the droplet is, and I think that is a big mistake. This is a variable that will affect 40% or not. So I don't know how to I didn't understand why it's 40%. Yes, but they didn't show us the variable.
Other questions?
So, that's the reporter. Can you summarize how you explain that's the final size of your the droplet?
Final size.
Using very briefly, using one sentence.
Here, the final center droplets, we define it as an average of 4 to 10 droplets in the center. So for here, we chose 4 to 10 small droplets here and use image ray to calculate this radius, and we got our data.
So it's an average, so there's some distribution. That means.
Because we just, for the final droplets, we just see it is close to 0. We didn't get, the exact number is not important at all.
So perhaps opponent and reviewer, do you agree with this method?
I cannot understand what is the report talking about.
I personally think that it should be defined as after the ring, which is where the concentration is higher, is completely disappear, and the size of final droplets. And I think you should choose the medians and to do the average many times, and that will make the result more accurate.
Okay, I would like to ask the reporter, can you tell me what is the Bernoulli effect? That's basically
This shows how the Bernoulli effect is. And when there is a surface tension gradient, the Bernoulli effect will cause the force that make the water molecules be cooled.
what is it? Okay. Okay, so on the opponent, you mentioned about the color effect, right? Color. Yeah, color effect.
Yes.
So can you tell me what's the color effect?
I think I didn't mention it. I just say what I see after.
Okay. But okay, the same thing
surface tension and the drop and the relationship between surface tension and the final drop. I think it kind of shows the relationship between these kind of variables.
Okay, so how about the viewer?
I think the marine gain effect is about liquid with a high surface tension pulls more strongly on the ambient liquid than the one with the low surface tensions. So this is why the ring, which I mentioned before, where the concentration is larger, will be completely broken.
Okay. There's no other questions from viewers. It's a time for story. Okay, please raise your scoring form. 6, 7, 6, 7. Sorry, this one. 6, 6, 7, 6, 7. The opponent. 6, 7, 5, 5, 6. Finally, for the reviewer. 7, 9, 7, 6, 7. Is there any comments from the viewers?
I think one comment. I think you should not talk about theory that you don't really understand. We need to talk about what you understand. The equation is very complex, and the phenomena are also very complex.
Okay, we again take 10 minutes break.